Let's begin this story not in the distant future, but now. A moment where the Earth is fragile. Climate change, overpopulation, resource scarcity, geopolitical instability. Our species stands on the edge of a critical turning point. And with it, a timeless question resurfaces. Can humanity build a second home beyond Earth? And if so, where? Among the many celestial bodies in our solar system, one world stands apart as the most promising candidate. It's not Earth-like by default. It's cold, dry, and hostile to human life. But it's close. It's reachable. It's Mars. And now Mars has become the canvas for one of humanity's most ambitious ideas, terraforming. Terraforming isn't science fiction anymore. It's a real scientific pursuit. It means altering a planet's atmosphere, climate, and ecology to make it habitable for Earth-based life. It's not just about putting up domes or living underground. It's about turning an alien planet into a living, breathing ecosystem. But before we begin the step-by-step breakdown of how this Herculean task might unfold, we need to understand why Mars and what the red planet offers us and challenges us with. Why terraform Mars and not somewhere else? Venus is closer to Earth in size and gravity, but it's a nightmare of crushing pressures and sulfuric acid rain. The Moon is nearby, but it has no atmosphere and virtually no magnetosphere. Jupiter's moons like Europa and Ganymede are intriguing, but they're far, cold, and bathed in radiation. Mars is the sweet spot, not perfect, but possible. It has 24.6-hour days, seasonal cycles, polar ice caps, gravity that's about 38% of Earth's, enough to potentially sustain bone health with support, and plenty of carbon dioxide in the atmosphere, key for plant life and greenhouse warming. But most importantly, we've studied it. We've mapped it. We've landed probes, rovers, even helicopters. We know its terrain, its dust storms, its underground water, and most crucially, we've begun dreaming of building something there. The first challenge is understanding Mars' hostility. Before we jump into how we can change Mars, we must respect what we're up against. Mars is a desert world. Its atmosphere is a 95% carbon dioxide, but it's incredibly thin. Standing on the surface feels like being 35 kilometers above Earth. There's virtually no oxygen. The average temperature hovers around minus 63 degrees Celsius. That's colder than Antarctica all the time. And then there's radiation. Mars has no global magnetic field. Cosmic rays and solar particles rain down on its surface constantly. Any human living unshielded on Mars would get a deadly dose in a matter of weeks. The planet's gravity, while enough to hold down some atmosphere, is not strong enough to retain lighter gases like water vapor or nitrogen long-term unless we create artificial containment or consistent replenishment systems. Lastly, the soil, called regolith, contains toxic perchlorates, which would have to be broken down before growing food safely. In short, Mars is not ready for life, but life might one day be ready for Mars. Terraforming, a century-long symphony. Terraforming Mars will not happen overnight. It is not a 10-year project or a single agency's mission. It's a multi-century planetary engineering effort that requires cooperation, dedication, and breakthrough technology. Think of it like planting a forest, not for ourselves but for the generations to come. So how do we begin? We need to go in phases, each one building on the last. The transformation from red world to blue-green Eden will involve 4 key stages. 1. Warming the planet. 2. Thickening the atmosphere. 3. Introducing water. 4. Establishing a biosphere. Each of these is daunting. Each one would require entire industries, possibly AI-managed systems, robotic fleets, nuclear energy, orbital mirrors, genetically engineered organisms, and more. Let's now dive into Phase 1, the first real step toward making Mars a second Earth. Phase 1, warming the planet. The first step toward habitability is raising the temperature of Mars. This isn't just about comfort. Without warming, liquid water can't exist on the surface. atmospheric density won't increase, and photosynthetic life won't survive. There are multiple proposals, some grounded in current science, others wildly speculative but fascinating. Option 1. Greenhouse gas factories. The most discussed method involves building massive factories that pump greenhouse gases into the Martian atmosphere, primarily perfluorocarbons, PFCs, which are incredibly potent heat-trapping molecules. These factories could be robotic, solar-powered, and mass-produced using Martian resources through in-situ resource utilization. Over decades or centuries, these gases would accumulate in the atmosphere, warming the planet through a greenhouse effect similar to Earth's, but on purpose. Option 2. Orbital mirrors. Another concept is to place giant space mirrors in orbit around Mars, artificial satellites that reflect and concentrate sunlight onto the surface, particularly near the poles, to trigger the sublimation of frozen CO2. This would release more gas into the atmosphere, thickening it and warming the planet, a positive feedback loop. Option 3. Nuking the poles, Elon Musk's proposal. Though controversial, Elon Musk once proposed detonating thermonuclear bombs over the Martian poles, not to destroy them, but to vaporize CO2 and water ice, releasing them into the atmosphere and initiating rapid warming. While this sounds dramatic, it could accelerate the process, but it's politically, ethically, and environmentally risky. The long-term consequences of radiation and the public reaction to nuking another planet make this option unlikely, though technically plausible. Option 4. Artificial magnetic field at L1. One of the biggest hurdles to warming Mars is atmospheric loss. Solar winds can strip gases away without a magnetic field. A newer proposal suggests placing a magnetic shield at Mars' L1 Lagrange point between the Sun and Mars. This would create a protective bubble, slowing atmospheric loss and allowing warming processes to be more permanent. As these technologies are deployed, likely in parallel, the temperature on Mars would slowly rise. Ice caps would melt. Subsurface ice would thaw. CO2 trapped in regolith would be released. The planet would become hazy, more dynamic, and warmer. But warming is only the beginning. Once Mars is no longer frozen solid, we move to the next stage of transformation. Phase 2. Thickening the atmosphere. Now that we've increased surface temperatures, our goal is to build an atmosphere thick enough to retain heat, support human habitats with minimal protection, allow for liquid water on the surface, block harmful radiation. This requires increasing atmospheric pressure, specifically bringing it up to at least 0.5 to 1 Earth atmospheres. Right now, Mars pressure is less than 1% of Earth's. That means exposed humans would suffocate and their blood would boil. We need to add trillions of tons of gases to the air. CO2 and nitrogen. Mars has plenty of CO2 in its ice caps and soil. Warming will help release this, but it won't be enough alone. We'll need to find and release nitrogen, which is rare on Mars but vital for breathable air, alongside oxygen. It also adds mass to the atmosphere, helping with pressure. One possibility is mining nitrogen-rich minerals or importing nitrogen from asteroids or Saturn's moon Titan, which has a thick nitrogen atmosphere. This would be a massive engineering task but potentially feasible over centuries. Oxygen production. We can't just pump oxygen into the air. It's dangerous at high concentrations and must be balanced with other gases. But we can grow cyanobacteria and an algae, engineered to survive in harsh Martian environments, to slowly, steadily produce oxygen. Also, machines like MOXIE, already tested on the Perseverance rover, can extract oxygen from CO2 via electrolysis. Scaling this technology could help both atmosphere and human breathing systems, using genetically engineered microorganisms. Synthetic biology may be a key player. By designing organisms that thrive in Martian regolith, consume CO2, produce oxygen, or emit heat as a byproduct, we can seed the planet with life that transforms it from the inside out. This approach is slow but sustainable, and perhaps the most elegant. With Mars slowly warming and its atmosphere thickening, the next step is crucial, bringing water back to the surface. Without abundant liquid water, no biosphere can survive. It is the universal solvent, the enabler of life, and the foundation for any terraformed ecosystem. And the good news, Mars already has water, just not in the form we're used to. Martian ice, frozen oceans waiting to be freed. From orbit and ground missions, we've confirmed that Mars has vast quantities of ice locked in its poles and beneath the surface. The polar caps contain a mix of frozen carbon dioxide, dry ice, and water ice. Beneath the regolith in mid-latitude regions, there are the subsurface glaciers. Some estimates suggest enough frozen water exists to cover the entire planet in a shallow ocean, if melted. This means we may not have to bring water to Mars, we just have to unleash it. As the temperature rises from phase 1, polar ice and underground glaciers will begin to melt, releasing water vapor into the thickening atmosphere. In turn, this adds to the greenhouse effect, further warming the planet in a positive feedback loop. But passive release won't be enough. We'll need to actively engineer Mars' hydrological cycle, creating rivers, lakes, and oceans. Here's where engineering turns from atmosphere to terrain. Mars' ancient geography gives us clues about where water once flowed. Dry riverbeds, floodplains, and impact basins, like Hellas Planitia and Valles Marineris, can be used as blueprints for future water systems. 1. Melting ice on purpose. Massive solar mirrors in orbit could focus heat on targeted ice deposits. Underground nuclear or fusion-powered heaters might thaw subsurface ice. As it melts, it can be channeled into lakes, aquifers, or artificial reservoirs. 2. Constructing artificial waterways. Robotic systems and autonomous AI machinery could dig canals, dams, and catchment systems to control meltwater. These systems would prevent flooding and create stable freshwater environments. 3. Pumping systems for water circulation. Once water is present, pumps and siphons, possibly powered by solar farms or nuclear mini-reactors, could circulate it, preventing freezing and mimicking Earth's natural flow systems. The idea isn't to replicate Earth exactly, but to create a closed-loop water cycle where liquid moves, evaporates, condenses, and precipitates again. Artificial rain and clouds. Building the Martian water cycle. For Mars to have rain, you need sufficient atmospheric pressure, adequate humidity, temperature ranges that allow condensation and cloud formation. As CO2 and H2O levels rise, we might see clouds returning to the Martian skies. Eventually, controlled cloud seeding, using particles introduced into the upper atmosphere, could trigger artificial rainfall. This rain would reshape terrain, feed aquifers, and begin eroding dust, a vital process in making the landscape less barren and more fertile. With rivers flowing and lakes forming, the final phase of this stage would be the recreation of oceans, perhaps restoring the long-lost Northern Ocean that scientists believe once existed billions of years ago. This body of water, stretching across Mars' northern lowlands, could become the anchor of the Martian hydrosphere. Dealing with challenges, evaporation and freezing. Even with higher temperatures and a thicker atmosphere, Mars will still be much colder than Earth. Water could easily refreeze or evaporate into space unless measures are taken. Artificial domes may initially be used to trap water vapor and control evaporation. Pressure valves and vapor catchers in the atmosphere could recycle lost moisture. Magnetic shielding, like the L1 magnetic field discussed earlier, would help keep atmospheric gases, including water vapor, from being blown into space. It would be a dance between engineering control and natural balance, letting Mars become more Earth-like while gently guiding it there. Introducing plant life seeding the soil. With water systems in place, we can begin preparing for life, the real goal of terraforming. But Mars soil is not ready for Earth organisms. The regolith problem. Martian regolith contains perchlorates, toxic chemicals that can disrupt thyroid function in humans and are hostile to many life forms. These need to be broken down or neutralized. Solutions include bioremediation, using engineered microbes to detoxify the soil, e-filtering systems to clean harvested water and soil, creating layered grow beds, using imported earth soil in limited quantities. Once zones of safe soil exist, we can start small with hardy genetically engineered algae and bacteria. These pioneer species would do the work of fixing nitrogen, producing oxygen, and enriching the soil over decades. Phase 3, building the biosphere. With water flowing and the land slowly becoming fertile, it's time for perhaps the most beautiful and delicate step of all, creating ecosystems. This phase would span generations. It would begin with microbial life and eventually culminate in complex forests, animals, and perhaps human cities not enclosed in domes, but open to the Martian air. The terraforming ladder of life. Step 1. Microbial colonies. Specially designed extremophiles would be deployed across the planet to stabilize soil and pump oxygen into the atmosphere. Some might be designed to glow under UV light, creating glowing biofields that mark early progress. Step 2. Lichens and mosses. Once microbes take hold, we'd begin introducing non-vascular plants, organisms that can survive harsh environments and begin trapping moisture and nutrients. Step 3. Grasses and vascular plants. With enough soil buildup and water cycling, hardy plants like grasses and shrubs would be planted, first under domes, then in open areas. Step 4. Forests and wetlands. As oxygen rises and temperatures stabilize, we could begin planting forests in temperate zones and marshes in lowland regions where water collects. Step 5. Insects and small animals. Pollinators, decomposers, and other essential microfauna would be introduced to manage plant reproduction and nutrient cycles. Step 6. Complex life. Eventually, genetically selected or engineered animals, including birds, mammals, and amphibians, could be introduced to fill out the ecosystem. This vision is breathtaking. A red planet turning green, rivers carving canyons, rain falling on alien soil, trees whispering in the Martian wind. AI and automation, terraforming's unseen workforce. Throughout all phases, artificial intelligence, robotics, and autonomous systems will be indispensable. AI could monitor climate, optimize oxygen production, and detect threats to growing ecosystems. Drones might plant, pollinate, or inspect flora. Self-replicating machines could build and maintain infrastructure, from solar arrays to water systems. Humans may guide the mission, but AI will execute it. With a breathable atmosphere slowly forming, water cycling through rivers and lakes, and the soil alive with alien green plant life, Mars is no longer just a red wasteland. It's a living world in transition. And now comes the moment that many see as the true goal of terraforming, establishing permanent human civilization. But this final phase is not just about engineering. It's about ethics, identity, survival, and the ultimate future of our species. Let's explore what it would take to make Mars not just habitable, but home. The first true Martian cities. Long before full terraforming is complete, humans will already be living on Mars in pressurized habitats, underground bunkers, and domed colonies. The first settlements will likely cluster around essential resources, near equatorial regions, where sunlight is abundant, close to subsurface water sources, on relatively stable terrain for construction, possibly in lava tubes, natural underground shelters perfect for radiation shielding. But as terraforming progresses, These bubble-like colonies will begin to expand. Gradually, some structures won't need sealed domes. Buildings may begin incorporating windows, gardens, balconies. Streets will be lined with oxygen-producing moss and trees. Eventually, you may step outside your Martian home in a pressurized suit, not to survive, but just for comfort. The line between Earth and Mars will begin to blur. Designing for a Martian lifestyle. Life on Mars won't be identical to life on Earth. The gravity is only 38% of Earth's, which will reshape everything from architecture to biology. Children born on Mars will develop in lower gravity, possibly taller, with different muscle and bone density. Exercise and nutrition will be critical. Over generations, Martians may begin to diverge physiologically from their Earth ancestors. Martian cities will look different too. Structures will be built to conserve heat. Transport systems may use maglev tubes or autonomous electric vehicles. Agriculture will likely start in vertical farms, but expand to open-air fields as conditions improve. AI governance systems may assist in resource management and environmental monitoring. This will be the age of planetary urbanism, humanity designing a new civilization not on Earth, but from scratch on another world. AI, the architects and guardians of terraforming. Artificial intelligence will remain the hidden backbone of Martian transformation. While human settlers adjust to life on the surface, AI-controlled systems will still manage climate balance, monitor oxygen and carbon cycles, repair infrastructure, prevent ecosystem collapse, simulate planetary models to test future outcomes. If Earth governments or agencies begin to lose focus over the centuries, AI may be the only consistent force ensuring the terraforming process continues. It's possible that the final stages of Mars transformation will be overseen by intelligent systems built by humans but operating independently. In that sense, AI will not just help terraform Mars, it will be the silent shepherd of an entire new biosphere. Ethical and philosophical questions. Before we crown Mars with forests and cities, we have to ask, do we have the right? Terraforming isn't just engineering, it's rewriting a planet's destiny. What if Mars had primitive microbial life still hiding beneath the surface? Do we destroy it with Earth biology? Do we risk extinction of alien species for human comfort? And beyond biology, what is our moral responsibility to Mars itself? Is it ethical to change an entire world for our needs? Or do we owe Mars the chance to remain as it is, raw, alien, untouched? Some propose a middle path. Create biospheres and oases without fully transforming the planet. Leave some regions wild. Let Mars keep part of its identity even as we build a new one. Terraforming also raises questions about inequality. Who gets to live on a second Earth? Will Mars become a haven for the rich or a collective home for all? Will access to this new world be earned, bought, or inherited? As we reshape planets, we must reshape our values too. The search for alien life along the way. One overlooked aspect of Mars terraforming is what we might find before we finish. As robotic explorers melt ice caps and dig into permafrost, we might stumble upon extinct or extant alien microbes, traces of ancient Martian life, or signs of unsurpassed civilizations, if such things ever existed. Terraforming is also a gateway to interstellar exploration. A thriving Mars base becomes a launch pad for missions to Europa, Titan, and beyond. From there, we may eventually send generational starships to Wake Proxima Centauri, TRAPPIST-1, or even further. And if we do, what happens when we find someone else out there? Will we terraform again? Will we colonize other life-bearing planets? Or will we finally see the universe not just as territory to reshape, but as a living mystery to respect? The final vision, Mars as a living world. After centuries of effort, robotic, human, and artificial, Mars may one day stand transformed. Skies hazy blue instead of pink, clouds casting shadows over lakes and valleys, Winds blowing through rustling forests, cities glowing in the twilight, powered by clean energy and protected by AI systems, animals roaming artificial ecosystems, human children running under a Martian sun, free of suits, breathing air from a world we once called dead. It won't be Earth. It will be Mars reborn. Terraforming is not just a technological dream, it's a civilizational challenge. It's the ultimate act of hope, planting the seeds of life in a place where once there was none. A monument not to conquest, but to care. And if we succeed, it may prove that we are not just a species of Earth, but a species of the cosmos. That our legacy isn't confined to one blue dot, but written across the skies of many worlds.